So good morning, everyone. This is Chen, an applied scientist and tech lead from the query understanding team of Amazon Search. And today I'm very happy to introduce our work about robust caches for Amazon product search roles. Okay, so first of all, let's say what is Amazon product search engine. Here's a snapshot of the Amazon product search engine, and the customer type in the keywords like Nike shoes. And the product search engine, we're trying to use some models to understand this query, like what is intern and what is attribute inside these keywords, and then use all this attribute to push it into our matching model. And the matching model, we're trying to get all a large set of candidates that match these keywords, and then pass through the ranking model. And the ranking model will rank the products based on the relevance between the keywords and every product. So that is stuff that is shown to the customers. So let's look into this product search engine. We know that the product search engine, as I just showed, that the product search engine contains so many different components like query understanding, matching, ranking, and some other models. And in all these components, we have so many different models like query attribute extraction model, query intent classification model, and query write model, or semantic product search model. And all those models are very large scale models. For example, the query write model, semantic product model, or the query intent classification model, we are using very heavy transformer or BERT-based models to encode the query to be able to have a very accurate output of this or accurate understanding of this model. So we are facing a problem of the latency is too high for the product search engine. And the traditional way or the common way or the widely used way of scaling up the product search engine or all these models is to use cache. So that we cache a large number of keywords and their corresponding output. So that when the next time the customer typed into some keywords, and we directly use this cache to retrieve the result. If it's not missed, we find something in the cache, we just return the stuff in the cache instead of going through all these heavy models. But there are several big issues for the traditional cache, that with the increase of the size of the keywords, the cache size also increases exponentially. So our search engine cannot handle very large scale of the cache. And also there are a lot of typos and errors in the keywords. And all those typos and errors in the keywords creates very high redundancy for this cache. For example, there are like Nike or Nike shoes or some error, some grammar errors in this word, and all these are very popular keywords, and we cache it. Actually, these keywords belongs to the same keywords, and so it's a waste of the resources of the cache. And there are also some challenges about the semantic meaning of the keywords. So there are like maybe very different keywords. They have exactly the same semantic meaning. They should return exactly the same products. And so all those types of keywords should also be appear only once inside cache. So we know that traditional cache has all those problems. We have to fix this. So in Amazon Search, we proposed a new cache. It's called rows. The long name of this cache is called robust caches for product search. So this proposed rows is a robust cache It can do constant time retrieval and constant time memory usage for arbitrarily large indexing size. And it's robust to typos and grammar errors. And it's also robust to semantic information. So whatever semantic meaning we can handle it by using this roles system. Okay, so this is a storyline. The storyline is very simple. So in the next step, I will introduce the roles framework. So basically, I will introduce the high-level structure of roles, and then I will introduce some offline and online experiments that we did, and how do we deploy this system in the real-world Amazon search production search engine. Okay, so the role system contains two phases, also two processes. There's an offline building process. So the offline building process is actually the process of constructing this hash based on a data set that we want to cache. So the process is like this. We have a data set of keywords or query, like Nike shoes or Coach bags. And we first do tokenization and vectorization to transfer all these keywords from string format to sparse vector format. And then after we have this vectorized information, we goes to a black box stuff called locality sensitive hashing to construct hash tables. And those hash tables can be regarded as a cache structure that I just introduced before. So after go this process, we actually constructed the row structure, the cache structure. And then the next step is the online retrieval phase, so online retrieval process. So basically, when a new keywords comes in, we use exactly the same process of tokenization and vectorization to transfer the string to the sparse vector format. And then once I have the sparse format, I will go to exactly the same hashing process to retrieve inside the hash table to get the candidate. So this is a framework, and there's a fancy black box structure called hashing, called location hashing. So let's get a small detour to see what is location hashing. So hashing, we all know that it's a function that maps a vector to an integer. And the locality sensitive hashing means that this mapped integer or hash value has some relation with the similarity between these two data points. So that for these two data points, their hash value, the probability that these two hash value is the same is proportional to the similarity between these two data points in the original space. And the similarity here, it can be any similarity matrix. It can be like lexical similarity. It can also be like semantic similarity between two keywords. And we can understand, or we can find that in this equation, that the similar items are more likely to have the same hash value under the locality sensitive hashing function. Okay, so here's an example. We have 6 data points. We want to construct the hash table. And hash table on the left is likely to be constructed by the locality hashing because all the similar keywords that go through the same buckets, they are having the same hash value. But the table on the right is unlikely to be constructed by the locality hashing because there are some unlikely event happened for this hashing process. Okay, let's go back to the roles framework and let's use this. Right now we know what is localism hashing. Let's use a small example to show what's going on here. So let's say I have four keywords, and one set of keywords is Nike shoes and the other is Amazon. So I push it into three hash tables under the location hashing, and we construct these three hash tables, and we can see that in some hash tables, the similar keywords are mapped into the same location of the hash table. And then in the online retrieval process, we have new keywords that is called Nike shoes, Nike shoe. So we use location hashing to get the corresponding location in different hash tables. And then we get the entire set of all the candidates in each location of all these hash tables, and then we count the number of appearance of each items in all these candidate sets. And we found in this case that the Nike shoes appear 3 times in these 3 hash tables. So the Nike shoes is returned for Nike shoe. That is the query keywords. Okay, so this is the high-level framework. So I will hide all the math, all the implementation details in the paper. So if you're interested in the details, you can go to the table or directly contact with me about this framework. So let's looking at some experiment and success deployment. So we did offline experiment for this work. So basically we compared it with some traditional cache, and we also made up some cache using some continuous neighbor search methods. And we can see from this table that in terms of F1 and precision recall, in most of the cases that our proposed method is better than the other methods. And when we're looking at the retrieval time and the indexing generation time, our proposed rows also faster than all this existing method. We deployed this row system into our product search engine, and we use 2 examples to show that. The first example is for rows, to use rows for our query rewrite model, and the other use of the rows is for the prototype annotation model. So the query rewrite model, we compared it with the existing query rewrite system, and we find that in terms of coverage, precision, and measurement, our roles-based system is better than the existing system. And we also did online A/B testing, and we find that in terms of revenue and purchase unit and click-through rate, we also gained a lot compared with existing method. And for the prototype annotation, we compared with our online BERT model, that we find that the precision and also the response time is also a lot better than the existing model. And we also run A/B testing, and we find that it's reduced the defect rate a lot for the product search. Okay, cool. So this is overall framework of roles, and this is all the contents of my talk today. And if you have any questions, I'm very happy to answer, and thanks.